Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones.
Hi, I'm in Melbourne, Australia, and I'm here at EMC Technologies, one of the world leaders in everything EMC. I'm here with Rob. Thanks for joining us, Rob.
No problem.
He's from EMC Technology. You're an RF?
Test engineer, yep.
Yep.
We do all the compliance testing, emissions and humidity.
Yep. And we've got some awesome stuff behind this door and in the rest of the facility. We're going to check it out. Behind this door is about 1.8 million bucks worth of awesomeness. So let's check it out. Push the button,
Okay,
Rob.
here we go.
Let's go. Let's do it. Let's go check it out. This is brilliant. Absolutely brilliant. 1.8 million bucks worth of RF anechoic chamber. It's basically the biggest anechoic chamber for RF EMC testing in the Southern Hemisphere. And Rob's going to take us through it. This is brilliant. Fantastic. I love it. So we've got some sealing on the door here as well. We've got oh, that's actually it's
not metal.
It's a conductive impregnated.
And I guess on the door you've got the more fingers.
Yep, and they made up with
slits into the.
Wow, brilliant! And it actually is a big concrete channel.
Yep,
down there, and
right,
and this floor lifts up. What's the purpose of the floor lifting up?
Just so we can drive the vehicles in.
Just drive vehicles in, and then it allows the seal around the bottom, of course, because this is lower than the floor level and then the base of the door. Right. So there was no way you could really seal the bottom of that because you would probably have bad sealing around the bottom of the door.
We measured it. We got about 80 dB attenuation across the whole frequency range inside the room, which is what we were after. Which is a fair bit. It's enough to cancel pretty much everything we need out.
And who was it manufactured by?
Franconia.
Franconia, German company.
Germany, I believe. Yeah.
Yep. And that's one of their other facilities, is it?
Yeah, I'm not sure where that photo was taken,
right.
But haven't actually been.
Tell us about that one. You mentioned there's something about a plane. They were testing about a.
Yeah, I think there was one in China. They made one that was a fully anechoic chamber, which meant there's cones on the bottom as well.
Right.
And it was big enough to fit in a jet fighter.
Jet fighter. So they had it hanging from the roof, and then.
Yeah, that's right. So another scale.
Fantastic.
Up again, yeah.
Right, but this one is pretty darn big. It is it is massive. That's probably 20 meters tall total would be my guess. And then inside the chamber would be around about 15 meters, as I've mentioned, from the floor to the top of the cone, roughly, or maybe even to the roof.
That'd be about right.
Yeah, something like that. And the door is very cool. It's very Cold War-ish kind of.
It's very solid, isn't it?
It is very solid indeed. I like it. No wonder. I'm surprised this thing only cost $1.8 million actually, compared to that, $1 million for that robot arm you've got in there.
That's probably the chamber, but then with the test gear that goes with it.
Oh, right.
Like
okay.
The mast and the fibre optic system, the camera system.
Right.
Probably all on top of that as well.
Yeah. Right. So that was just the physical build of the chamber.
I believe so. Yeah.
Right.
Yeah. But that's obviously the bulk of the cost.
Yep.
Yeah.
And that floor's capable of handling many tens of tons.
It's about 8 or 9 tons, I think, to go in there. Yep. So it's a good sized vehicle.
Yep. Well, we could actually drive a truck. Yeah, you could drive pretty much any
3-ton truck or something. Probably fit in there.
Yep.
Fine.
Brilliant. And this is pretty much the coolest thing I've ever seen. It is just wow, is all you can say. And you can actually see the size of the depth of the cones here when you actually stand side on inside the door, 2.2 metre depth, and That's how they get away without the ferrite shielding.
Yep.
It's brilliant. You can just drive trucks in straight through the roller door.
This is our control room for the indoor OATS, indoor open area test site.
So that's essentially what it is an indoor open area. Exactly. It's designed to duplicate an open area outdoor site.
Yep. Precisely, just to avoid all the ambience. So this is our test receiver that we use here. It's good for up to 6.5 gigs.
Yep.
Which covers most testing, but nowadays we've got quite a lot of work going up to 18 gigs, 12.5 gigs, 18 gigs, and even for the FCC we're going up to 40 gigs.
That's what the chamber's capable of doing?
Yeah, well at 40 gigs,
right.
Distances isn't such a big thing, so
got it.
You're not going to get the reflections and that so much.
Yep, and you've got
at the levels we're measuring, it's not a big deal.
And you've got a pan tilt video camera.
That's
here.
right, it's all remote controlled from in here, so we can play around with it, monitor things as we test them.
Yep.
Make sure there's no fire or
right, okay.
or anything like that. Just to make sure everything's working really at this stage.
Yep. And this is, how old is this? When was it built?
Commissioned it just after Christmas this year. So it's been going for a good about 10 months. So
got it.
Yeah, it's still pretty new. Still finding little bugs here and there, but
right. Yep.
We've got it working pretty efficiently now. It's good.
What sort of bugs? What sort of problems would you get with these sort of setting up these sort of chambers?
Not many. It's small things like the fibre optics, setting them up properly, and just the way we like it, the way we want to use it more than.
For you customise it for your particular
that's right.
uses.
That fits our equipment and that sort of thing. Like the very high frequency stuff, the cables have got too much attenuation, so we have to actually do testing inside the room.
So you have to move the gear in there. And
so we move like that test receiver and we sit in there on a wee desk.
Would you shield the gear when it's in there?
No, again, it's only the really high frequencies, and they're very directional, as you can imagine. So we haven't had a problem with what we've been measuring.
Right. And you've got a very low-tech loop antenna there.
Yeah, loop antenna. It's got a wee preamp in it and that, so it's for 30 megs and under generally.
Right.
For magnetic fields. We've got over here. We've got a sort of a standard gain horn kit up to again 18 gigs, I think. So
so that's a little feed horn?
Yeah. Yep. So they've got a standard gain, usually about 30 dB over a small frequency range.
And that's just got an end connector on it? And
just all end connectors. We've got another one as well. Go down to about 1 gig of these.
Neat.
Obviously the bigger they are, the lower frequency.
Yep. Nice. And there's the internal door. It's not nearly as big as the external door that you can drive a truck through.
Yeah, that's right.
But,
it's a bit easier to open and close.
Yep. Ta-da!
There we go.
All right. Shall we take a look?
Let's go inside.
Oh.
I'm not sure what it's in here.
This is just brilliant. This is brilliant. There's no other word for it, really. It's pornographic. Look at this. It really is. So tell us about this room. This is the brand new, biggest.
This is the OATS,
biggest in the Asia Pacific region.
Yeah, I'd say Southern Hemisphere maybe. Yeah.
Southern Hemisphere.
There's some big ones up in China and that, obviously.
Right. Yep.
But pretty much, we've got the turntable here, which we can control from outside the room.
Right.
We place our product, whatever we're testing, on the table.
Yep.
This test is a bit different. Usually it's laid flat. It's about 80 centimetre high table.
Right.
This is an intentional transmitter test. So we're trying to get into the sort of a bit of no reflections off the ground plane, sort of open space.
Yep. And is that a big block of foam?
Yeah, it's just polystyrene.
Oh, it's just polystyrene. Polystyrene block.
It's pretty invisible way up to the high frequencies.
Right.
And we used to use wood, but now that frequencies are getting up, any moisture in
the wood, I'd say would
causes an issue. Yeah.
Absorption issues. Even would it be absorption or would it be
reflections mainly?
Yeah, mainly reflections.
Yeah,
okay.
For sure.
Right.
Yep.
And these are incredibly deep. I cannot believe how deep these cones are. They're like 2 meters deep. They're absolutely 2.2 meters deep. Okay.
The idea is so we don't have to have ferrite tiles on it.
Oh, okay. So this isn't a ferrite tiled room.
Yeah.
Because it'd be massively expensive.
And too heavy, yeah.
Right, okay.
Complete structural.
Because this is like,
structure.
That's got to be 10, my abseil in heights, I reckon that's 15 metres actually, from here to the top of that roof.
That sounds about right.
About 15 metres?
That's 4 metres high.
Right, okay.
Well, it's probably 5 metres to the top.
Right.
The mast.
Oh, right, so,
Sorry,
okay.
The mast, yeah.
Yep, so the mast here, tell us about this.
Yeah, that's all computer controlled again from the outside. It's all fibre optic link. We can control the up and down,
yep,
and also the polarity. So most tests are done the antenna horizontally and vertically, just to cover all the bases.
Right, so that'll just rotate that around on command, and you can raise it up to 4 metres high. Is that part of the standard? Is it?
That's right. Because the reflections off the ground plane, we got to go all the way up.
Right.
To 4 metres.
Okay.
It's set up for a 3 metre distance at the moment, roughly. A little bit closer actually.
Could you solve the reflection issues by putting those tiles you've got over there in front of the? Would that be a common practice?
That's where they do go for some tests. The tests above a gig, they want the testing done in free space. So the best we can do is put tiles in the front so there's no reflections.
Got it.
But the standards call for the ground plane. It's supposed to be there.
Okay.
They take the reflections into consideration.
Oh, they take it into consideration in the standard. Yeah. Got it.
When we calibrate the room, we put a transmitter on the turntable and have the antenna back at our 10 metre mark.
Right.
And measure the standard field off. And we measure the attenuation between the two antennas.
Got it.
And it's got to be within a certain theoretical level across the whole frequency range.
Why is that off axis? That mark? I presume that's another mark to put the antenna.
Mark, yeah, I'm guessing just because of you still get certain bit of reflections in that, and probably the standard calls up. You have to have a certain distance to cones and things like that. So maybe it's too close.
Yep.
To the back, but Franconia, who built it, they would have checked all this out first.
Sure.
Probably found that this was the optimum position.
Right. And what's the access port down on the floor here?
At all it's got a couple of points there. We've got I'll take one up. So we've got power into there.
Nice.
And we've got the fibre optic link to control the mast.
Okay. And it's a fibre optic link because you obviously don't want any
no emissions at all. Yeah.
Zero emissions inside the chamber unless you absolutely have to.
That's right, unless there's an auxiliary equipment or something in here.
And once again, that is all RF shielded as well around
Yeah, that's right. Yep.
Yep.
So we can put some bit of test gear in there, or usually up there, but if we need to.
Yep.
And we've also got patch panels. We've got cables going from here back out to the control room.
Okay. Right. Nice. And is this all built on a wooden? Looks like it's all built on a wooden base.
Yeah, it's raised up from the concrete floor by about a metre, maybe not a metre. So.
Yep. Is there a reason for that? Purely to get cables under, maybe?
Oh yeah, for sure. Yeah. That'd be the ideal, I guess.
Right. And what are these actually? What are these ones?
It's cardboard.
These are cardboard again.
Other ones, yeah.
Right. And they've got an end cap.
Yeah.
I don't know.
Just for protection.
Just for protection.
Yeah.
Right. And why the different colours?
Alrighty, this is our main door. The red ones are the doors, the ones that move, and the yellow is just outside of it.
Yep.
So there's one up there as well. We can pull those cones out.
Excellent.
Got a big extractor.
And then, another extractor for testing cars and trucks, because you are going to install a huge turntable in here,
we want
aren't
a huge turntable with a dyno on it, so we can test them running.
Right.
At the moment we only do emissions, but we're looking at doing whole vehicle immunity testing.
Whole vehicle immunity. So the manufacturer drives their car here and you
we
bombard
point an antenna at it
and bombard it with how many volts per meter?
Yeah, well, we can go 100 volts is
100 volts per meter?
roughly the standard one, yeah.
All right.
But it varies depending on the car and that. They want higher than that nowadays, 200, sometimes 300 volts
per
meter.
So there's no ferrite tile in here at all. You just found you didn't need the ferrite.
No, the cones again, because they're so long.
Right, they're so.
It's the actual dimensions of the cones.
Physical dimensions, right?
Define what frequency ranges they work at.
So what range is this room capable of?
I think it's up to 18 gigs again. So down
18
to
gig. Yep.
So that 30 megs is the starting frequency for the this type of testing. So from 30 megs up.
Yep.
To I think 18 is usually the standard. Maybe even a little bit higher. I'm not sure.
Right. How is the turntable going to be installed in here?
We've got a big pit underneath, so we'd have to rip up the.
Okay, you'd have to take it up, and that'll be permanently installed.
Yeah.
Right.
Yeah. There's about a 6-foot pit.
Oh, okay.
Down under there.
Right. Because you'd need a fairly beefy turntable to turn a truck around.
With the dyno and that on there.
Yep.
I think it's all got to move and that, so you don't get any cables caught up.
How would you do a dyno without generating electromagnetic interference?
You could do a sort of test with it just running and look at.
Oh, and you could take that spectrum
just do an ambient and work around it.
Okay.
Yeah.
Would you do that if you had gear in here as well?
Yeah, that's usually quite often in the military and auto standards they require us to do an ambient test.
Right.
But we know there's nothing in here, so.
Right, but they want that as part of the documentation, though.
That's right.
Yeah.
Yeah.
Got it.
Yeah.
Excellent.
Cool. We can. I think it's rated up to about 8 tons at the moment.
It can hold 8 tons.
Yeah.
Wow. Nice. And what's the floor? Is it
It's just a sheet
steel?
Aluminium, is it? Steel?
Sheet.
Steel, probably.
Yeah, just rolled sheet steel, I think, by the looks of it.
Yeah, it's on a metal frame, and
Yep.
I had another level of this as well in the bottom. So there's actually two layers of the metal.
Fantastic. And this is pretty much the biggest room in the Southern Hemisphere.
I'd say so, easily.
Yep.
Yeah.
And it's
not many of them around.
And it cost about $1.8 million, I heard, so not cheap.
No.
Wow. Can't believe the depth of these. The depth on these is just remarkable. It really is. So was it 2.2 metres?
Yeah.
2.2 metre depth. Brilliant.
Yeah, it makes our job a lot easier without TV signals and radio and all that sort of carry on.
Yep.
Yeah. We're finding out at our open area test site that they're just getting too hard. The digital TV stations were.
So that was a big problem. Digital TV.
Quite broad.
Yep.
Yeah.
Okay. Even in the middle of nowhere. Where was your open air test site located?
Luderberg Gorge, which is near Bacchus Marsh.
Right. How far? Where's the nearest?
About 40-minute drive from here.
And where was the nearest RF source to that? Do you know?
The few cell phone towers around the place and that. There's a township not far away, so the TV was there.
Right.
Yeah.
And that's why you built this indoor facility, because it's.
We'd have to go into the middle of Australia to get a
to get a better site.
You can't avoid it nowadays.
Yep.
You can dig a big hole or something.
Yep. Although I heard we're probably a good chance to get the Very Large Array radio telescope. Contract. Australia's bidding against South Africa or something, and because we offer a whole bunch of open space in the middle of Western Australia, and I think one in New Zealand too.
I've heard they're all over the place.
Yeah, they're all over the place.
All over the world,
Yeah, and we're ahead of South Africa because we have a politically neutral environment. Let's say
a little bit safer, maybe.
Exactly. So. This is fantastic. Thank you very much for showing us around, Rob.
Yep, no worries.
Brilliant.
It's quite cool. The lights come down if we need to change the bulbs.
Oh, okay.
Press a button and they all drop down.
And they drop down.
Yeah. So they've thought of everything. They're all Germans.
German technology. We love the Germans on the EEVblog.
Our semi-anechoic room, mainly for military testing.
Yep.
We do component testing on the metal table over there. Emissions and immunity for military, we usually get up to about 200 volts per metre fields, so it's pretty important that we have a nice sealed room.
Okay, so this is just a standard emissions anechoic chamber?
Pretty much, yeah.
Right.
So it's a fully sealed metal room. Semi-anechoic means there's no absorption on the floor.
Right, okay.
Which is why that's open. Right. And all the tests are generally at 1 metre anyway, so...
Right, okay. So the floor doesn't really matter in a thing like this?
Not at that level, no.
Right,
not at 1 metre. It's when you get into
but it is metal, though. It is actually shielded, so we're in a Faraday cage, essentially.
Exactly, yeah.
Right.
That's right, yeah. So we don't get any ambience from outside, no TV signals, things like that. And for immunity as well, we need it sealed because we don't want to interfere with anyone else. At 200 volts per metre we can...
Right.
Especially when we've got the airplanes flying over Melbourne Airport just up the road. So that means our test equipment can't affect the measurements we make.
Got it.
That's pretty much it.
Yep. Yeah. So that's the rule generally. Only the device under test is inside.
Yeah, that's what we're trying to do. It's not always possible because usually the device needs a lot of auxiliary equipment. Yep. And so it's quite hard to isolate the two sometimes impossible.
Right. Excellent. And this is a copper table.
Yeah, usually the automotive and military standards call up metal tables.
Right.
Because most of the products are connected to big metal chassis or whatever, so it's their compromise on how they do that. Okay. It standardises it between all the other labs as well.
Right. And how is the earth arranged? This is just a localised
This is just
earth? It's not mains earthed? Or
building ground.
Oh, it's actually building ground. Okay, so it is mains earth.
So it's a safety thing as well.
Oh, okay, got it.
Safety ground.
This isn't a terribly big room by your guys' standards?
We found out we had so much work on that we needed another room that we could do this testing.
Right.
So we prefer to use the CISPA 25 room.
Yep.
But if we have to, we can come in here.
Rob, what have we got here?
Alrighty, this is our GTEM. Basically a strip line.
It looks like a giant feed horn, but it's actually a strip line.
Yeah, similar principles, I guess. But so when we look inside, it will become obvious. So there's 3 tests we do in here. There's emissions from a product.
Yep.
So we can actually measure the RF coming off something and measure it down at the bottom with a spec-an or receiver.
Yep. So you can do transmitting products. And have a receiver.
Or just spurious as well, so unintentional noise more.
Yep.
Yeah, and the opposite, where we can test for susceptibility, we can get some really high fields inside between the septum and the ground.
Yep.
And we also calibrate electric field sensors.
Right.
So we get a known sensor, we can generate a known field, and put in the other meter, the new meter, and calibrate that against it.
Right. And this is like a miniature version up the top here.
Yeah, that's right. Yeah.
So this is pretty much just a...
Let's see inside of it. Alright. Can you see anything? So there's a septum there.
Yep.
And we get the field in between there. There's also the same at the bottom.
Right.
So it's a
nice.
It's a tri-plate.
And so do you use this much? Is it a commonly used bit of kit around here, or is it?
We're starting to use it more. The standards are starting to allow for this sort of products to be tested in here. Probably not as much as we want at this stage. So you can see there's just a connector in there.
Yeah, it's actually a connector, so it's purely it's purely passive. It's a
yep.
And let's take a look. And up the end here, we've of course got our
the magical cones.
RF Anechoic cones
they just stop reflections back down, just to give it a more uniform field.
Got it.
So you can probably see in here.
Yep.
You'll have to walk around in here. So we've got the septum here.
That's called the what?
The septum, I think.
The septum. Okay, right. All right.
And that's connected to the centre pin of that.
Right. So that actually goes right down to the centre pin of the RF connector at the end.
That's right. Right down narrow, and all the rest outside is ground.
Right. Is that that's mains earth? I take it. Yep.
It's all, must be. Yeah, just for safety reasons. Again.
Okay. Yep.
Because if you accidentally put this at a voltage, you sort of.
Yeah, sure, you're in trouble. Okay, and you only need the cones at the end here.
Yeah, that's right. Because it's only for really small equipment. So we usually put them right in the middle.
Right.
And we get the field.
Yep.
Generated between the plates.
Got it.
And vice versa for emissions. This will pick it up.
Yep.
And there's all these conversion factors to bring it back to.
Nice.
Different things. Yeah.
I like it. And the seal on the door here, as with all your chambers, is pretty well.
Yeah, well that's
pretty well
where
RF.
all the leakage happens.
Yep.
In
Yeah.
these chambers. Yeah.
Right. And there's a little window on it too, so you can actually get in there and see things under test.
Just a little wave guide. So.
Yep. And this will go from what frequency? DC to daylight, pretty much.
Yeah, pretty much. It goes right up to. We've had it up to a few gigs.
Right. But it will do low frequency stuff as well.
It goes right down. Probably not DC, obviously.
No, yeah, exactly.
But very low as well.
Right.
Yeah.
Well, some RF designers would say a couple of gig is DC. So, you know.
That's right.
Yeah.
We're not quite at that level, but.
Right. And you've got no shortage of rooms here. You're in the same room here. We've got another little.
This is not much bigger than a closet.
That is very closet size, but it's.
So we do electric field meters in here, just in a higher frequency range. We get up to about 18 gigs.
Oh, okay.
When
Right.
we do the E-field meters in here.
So how many anechoic rooms have you got here, all up? There's a lot.
We're up to lab 12, so we've got at least 12 or 13 of them, yeah.
And they've all got specific uses, or
Pretty much, yeah. A couple of them double up, but generally they're all specific.
Got it. Excellent. And once again, we've got an RF, the RF connectors, the patch panels on the wall, so you can penetrate the chamber.
All the chambers have the AC is filtered as well, so if you need AC inside, we have to
Got
go
it.
through these filters. They're usually up to 30 megs.
Oh, okay, right. Yep.
A few K up to 30
Yep.
megs or so, 100 megs.
That's if you are powering gear inside there.
That's
or
right,
is it
yeah.
sometimes better off to power it from batteries or something in there?
Oh,
Is
that depends on the product, yeah. If it's
Right.
battery powered, then yeah, for sure.
Yeah.
Yeah, batteries aren't susceptible to anything. So.
Exactly. Batteries just work. You don't have to filter anything.
But they
It's
go
nice.
flat.
They do. So how long would it take to test something in these chambers typically? It depends on the product.
Oh, it varies, yeah.
Yeah.
I mean, some tests we come in and we're done in a couple of hours.
Right.
But to do a full sweeper test, you're generally looking about a week.
Got it.
Yeah.
So this is effectively this is the strip line that's effectively inside that beastie in there.
GTEM, yeah. Yep. So we use this as automotive testing for just very small automotive components.
Right.
And also we use that for testing fire alarms, little fire
okay.
alarm detectors.
Yep.
We put them in there and put a wee field across them and make sure they don't go off or
Right.
give a strong thing. So again, you
So
can
that's
see
a 150 millimetre strip line. There you go. And it's just an end connector on the end? Or
Yep.
no?
So that's connected to, yeah, that's right, connected to the centre pin of the
Yep.
end connector, and the rest is grounded.
Right.
Generate the field in between two plates.
So you would move this inside the anechoic chamber? Right, of course.
That's right.
Yep. And where would the product actually be placed?
We try and get it in the middle. There's a couple of different tests. If it's just a small product, we'll put them in the middle.
Right.
But another part of the testing is we test just the cables. So imagine this on the floor, obviously.
Yep.
The product's up there, and you lay the cables all the way out to the power supply there.
Yep.
Because these are only for low frequencies, so lowish frequencies.
Right. What sort of frequencies are we talking about
we're
there for
looking
lunch?
a meg up to a couple of hundred,
Okay.
400
yeah.
megs. And at those frequencies, it's the cables that the RF's going to couple onto, not the actual product.
So Rob, these are your typical wideband antennas you would use for testing?
Yeah, that's right.
Can you tell us about that?
We use these ones for immunity testing. So we put a signal into it and test a product for susceptibility.
Right. So this is basically this is a transmitting antenna. Can they have dual use? Are they?
We haven't calibrated these ones
Right.
for emissions for receiving.
Right.
But there's no reason why not.
Yep. And that looks like a log periodic design, if I'm not mistaken.
Yep, it's actually called a bilog.
A bilog, okay.
Because
Yep.
the big ends here, they simulate a biconical antenna. And like
Right.
you said, this is the log periodic part of it. So we go down to about 80 megs. Yeah, roughly 80 megs up to 2 gigs. So it's a very broad, quite a broadband range. Maybe even down to 30 megs.
Okay, 30 megs, that's DC for RF engineers. I'm sure there's lots of RF engineers watching and they're going, oh yeah, I know all about that, but I can't pretend to, unfortunately. I am not an RF engineer. So it's almost black magic. No, it's not, but it's all that complex math, right?
That's it, exactly.
Yep. Better you than me. What's this room? This is significantly bigger than the others we've looked at.
Yep, this is our radiated immunity room.
Yep.
It's generally tested to a standard IEC 61004-3. And basically, we've got a transmitting antenna. We have our amplifier and signal generator outside, all computer controlled.
Yep.
And we feed it in and put the product down here on the table. And we can monitor it using cameras.
Yep. That's why you've got these set up, the cameras, and you can actually control those from different angles.
Yep, that's right. We can we set them up and monitor everything from outside, because usually the fields aren't too high. We're talking 10 volt per metre, 3 volt per metre, 10 volt per metre. So it's not huge, but we'd rather not be in here.
And not be in here at the same time. Okay, and you've got an exhaust in here as well. You can drive cars into here.
Yeah, we've tested a few big vehicles in here.
Yep.
Usually we do immunity, but also emissions as well on the vehicles.
Right.
It's just for investigation. We're not certified to do it.
Right.
But it's quite useful, sort of pre-compliance.
Yeah, those sort of pre-compliance things. Yep. It's just to make sure you're in the ballpark and there's a good chance of passing the actual.
Exactly. Yeah.
Yep. Test. Yeah. And this doesn't have a copper table.
No, this testing's for sort of commercial type stuff, so your computers and anything like that.
Right.
Basically what we do is calibrate just a 2-dimensional field. We make sure we get a uniform field here and place the product right on the end.
Right, so it's got to be on the end of the bench. So it can make a difference if you're 30 centimetres backwards or something.
Yeah, that's right. You lose a bit of field.
Right.
And we have to rotate whatever we're testing around, so all the sides and that.
Got it.
The cones...
Yeah, you've got them on the floor. And
they're just to stop reflections off there, and they will affect the uniformity of the field.
Right.
So that's the main reason they're there.
And these are ferrite tiles on the floor.
Yeah, don't get too close. They're all falling to bits on it.
Oh, right, no, that's okay. But and they're on the walls as well. Can you show us that?
Yeah, that's right. So we've got them all on the front and the back.
Right.
And the sides as well.
Okay.
And then we've overlaid the cones to get higher frequencies. So these guys, they go up to about a gig.
Right.
Roughly 30 megs to a gig. They're good for absorbing. And the cones are good for a gig and up to roughly 18, depending on their shape.
Yeah. So is that the secret to a good RF anechoic chamber? You need these ferrite tiles. You can't just have a metal Faraday cage.
That's right. You get too many reflections and cancellations and that sort of carry on.
Got it. Yeah.
And that's why one of the reasons as well we don't do emissions in here, because it's too. You get too many reflections and that. It's not a.
Okay, so there you go. The key is the ferrite tiles, which the ferrite tiles are actually all on the walls here. As you can see, this is the entry door where presumably they bring the cars in. Yeah, you can drive stuff in, and I assume that would be one of the major reasons why these things cost so much to set up.
Yeah, last I heard they were like $11, $15 a tile.
A tile. Yeah. Count the number of tiles, folks, and you can work out how much. So you've got power inside here as well. That's filtered.
3-phase and single phase.
3-phase, yep.
So
Excellent.
we can test all sorts of stuff in here.
Right, and the floor is actually a Faraday as well. It's metal.
Again, it's a fully
enclosed.
Enclosed room. Yep.
Excellent. And there's the patch panel where we can get the test signals in and out. And it's nice. And what is the foam made of? We're not really sure, are we?
It's just the sponge type stuff, but it's the coating that goes on it, which is does the absorbing. Right. And the sponge just gives it the shape.
Yeah. So it is literally a a sponge, folks. It's nice. Excellent. That's a great room. I love it. So is this your second biggest room you've got, or?
Probably second equal of the one we'll look at soon.
Right.
So, no, it probably is a bit bigger.
And you've got cardboard on the roof. They're actually not foam, they're cardboard, are they?
Different type, yeah.
Right.
A lot cheaper and easier to use, they're so much lighter.
Got it.
Yeah.
And why is the mesh up there?
I think that's a bit of a historical thing. I think they used to test a few things in here that generated a lot of heat.
Right, okay, and things fell off the roof.
Yeah, they were worried the tiles would come crashing down.
Okay.
Because it's all, underneath those white cones, it's all tiles.
Got it,
Yeah.
okay. Yep.
Yeah.
Excellent. So the whole thing is, although there are gaps in the tiles on the roof, though.
Yeah, that's right. I mean, it's tuned at trying to minimise the use of tiles. They figure the reflections from here aren't going to affect our field that we're trying for in the front.
Got it. And there's that antenna we looked at before, the wideband.
This guy's rated down to 25 megs and up to 2.7 gigs.
Right.
So broadband.
Nice. So you have a whole bunch of different antennas for different uses.
Yeah. This one is a broadband, but for the military and automotive, we usually split them up to get a bit better fields out of them.
Yep.
A bit more gain. So.
Nice. I like it. And this is pretty... Oh, it's not as good acoustically as the other rooms.
It's all the cones. You can sort of get it maybe down the end.
Yeah, down the end. We can actually talk into it and our voice just vanishes. But when they're in those rooms where you're fully enclosed by cones, whereas this one is not as much.
But that's not the purpose.
No, it's not the purpose. But you have had people here doing audio testing in various chambers.
Get very quiet rooms. Yeah.
All right. What sort of gear we got here, Rob?
This is our new flash spectrum analyzer or test receiver. As you can see, we're going from 20 hertz all the way up to 40 gigs.
Yep.
So it's very broad. It's specially designed to do EMC testing. It's got special detectors. It's got an averaging detector and a quasi-peak detector.
Yep.
And a couple of other. There's a new RMS detector and things like that.
Right. And if you have to ask the price, you can't really afford it.
Probably
much. Yeah, right.
It's not cheap, that's for sure.
Yeah.
Especially to cover those ranges.
Excellent. And what have we got over here? We've got a 250 watt L band amp.
Oh yeah, that's 1 to 2.5 gigs. We've got another 2 stretch all the way up to 18 gigs.
Right.
So generally we can pretty much get 200 volts per meter.
Right.
All the way up to 18 gigs, from roughly 30 megs to 18 gigs.
Fantastic.
Yeah.
I like it. And once again, the doors are completely sealed. They've got the full-on RF.
Well, I don't know what you call them.
Well, it's got a lip which goes into there, and then all the individual fingers on the. So
it's a lot better than just having the fingers touching each other.
Right. Got it. And when you're in there, you can't hear people scream? No?
No, it doesn't quite work that well.
when testing's not working, you can have some fun in there, beating your head against the wall. That'd be great. Right. And we're in yet another room. What do we got?
Okay, this is another semi-anechoic chamber, but this is designed around CISPA 25 specifications. Right. Which is automotive testing components, mainly components in here. You can't get a vehicle in, obviously.
So it's sort of one of those car computers,
anything,
or
any parts anything from the ECM to a console to gauges, any part of it, and we do emissions and immunity in here.
Got it. So what's this rig here set up to do?
This is an antenna for Ford's Ford specification.
Right.
And it's just a wee spacer.
Right.
But it's a little biconical antenna, and we inject our RF in there and wave it around the product, up to that far away from it.
Right. Okay.
And and we just check for susceptibility. So we're just simulating things like people using cell phones and that inside the vehicles.
Okay, yeah.
CB radios. If you're in a cop car or something, they've got some
they've got some pretty powerful
transmitters.
RF transmitters,
So we wave that around not quite wave. But
right, yeah.
we place it next to what we're testing and see what happens.
Got it. And I note the I've never seen so many RF beads,
Little ferrites, yeah.
little ferrite beads on a cable before. What's the?
I'm not too sure how they work, but they're
yeah, they're magic. You put enough of them on, and
yeah. So it's like if you've got the antenna there, you've got a big metal, but
you've got that's an antenna. So
exactly.
If you would have to space them a certain minimum or maximum distance apart to get your effectiveness, I would guess. Yeah.
Yeah.
Excellent. And once again, we've got a copper table.
Copper table, yeah, and it's grounded to the wall. So this is actually grounded to the chamber.
Right. Okay. So this is grounded to the outer walls of the chamber.
All the others have done that as well. Yeah.
Right. And why so many huge, big strips like that?
That's again caught up in the standard. You've got to make sure you've got a really good RF ground.
Right.
If you just had a little wire,
it wouldn't be good enough.
It'd be hopeless. Yeah.
Geez, well, you've certainly nailed it there with like a 8-inch wide copper straps going right to the back of the chamber. That's incredible. And you've got cardboard. Everywhere. These are like just cardboard. Can you take that one off?
Yeah, you can see we've got the tiles behind it.
Yep.
So they're, like I said, they're up to a gig. Good for
a gig.
Up to a gig. And these guys will go up to about 18 gig.
Right.
So we've got quite a good range in here.
So they would be like a carbon-backed, something like that. We don't know. It's a bit of a mystery. Magic.
I'm not sure. Yeah, I haven't looked into. I didn't have to look into it. So.
But it works.
Yeah, so, it seems to work really well. We get very good repeatable results.
Yeah. This isn't as acoustically. Oh, it's pretty good.
It's not the same though, is it?
It's not the same as the foam. No, it doesn't.
They're so much smaller, I guess.
Yep. But it's brilliant. It's a room made of cardboard. It's great. Cardboard and ferrite. I think I'm in the wrong business. EMC pays pretty well. That's not my hire car, unfortunately. That's my hire car. See ya.